Alright, now we have three vectors, and we put them into these column vectors to make a matrix. Okay, and we are trying to determine whether these three vectors are linearly dependent or linearly independent. And the tool we use is still the elementary row operations, reduce a matrix to row echelon form. So we start from over here, and then we see that we can actually just do it over here. This is the first entry over here is really the pivots over here. So we can do we can add the first row to second row and add it over here, and we can multiply -2 to the first one and add it to third one. Okay, so let's perform two actions together. Nothing is going to happen to the first row, 1, 2, 4. Add the first one to the second one, we have 0 and 12 and 4. Okay, and -2 times 1 is -2 plus 2 is 0. So this is good. And then -2 is -8, minus 1 is -9, and then -4 plus 1 is -3. Okay. Now we see common factors in rows, so we are going to risk scale. So we have second one over here, risk scale divided by 4, and third one over here we risk scale, and we have -3, and then we have something like this. We have 1, 4, 2, and 0, 3, and 1, and 0, and 3, and 1. Now this is not in the row echelon form yet, because we still have 3 over here. We're looking at these two rows. So we now see that we use -R2 added to R3. Okay, and that's what we have. We have 1 and 4 and 2 and 0 and 3 and 1 and 0 and 0 and 0. Okay. Now we can easily see that we have a leading one over here. Well, we don't have a leading one over here. We have a leading 3, but that's easy to do. Divided by 3, it's going to be the same thing. We don't have to do it, but if we want to, we can do it. Now, this column over here, this last column over here, does not have a leading one. So if we just have one column without a leading one, then these vectors over here are linearly dependent. In fact, this column over here without the leading one is linearly dependent on the vectors to the left. So 1 over here, this vector and this vector. So we can find out, so we know that over here that 2, 1, 0 is linearly dependent, on these vectors 1, 0, 0 and 4, 3, 0. What it means is that we can actually find two numbers over here such that this is true, 1, 0, 0 and plus b over here, and 4 and 3 and 0. And to do that, we can just multiply them out. This is going to be, over here is a plus 4b, and then here we have simply 3b, and we have 0. Okay, so we compare both sides. What we have over here is that a plus 4b must be equal to 2, and 3b must be equal to 1. Okay, so we have b is equal to 1/3, and a plus 4/3 must be equal to 2, So A must be equal to 2/3. Okay. So what it means is that now we have the following. We can see that 2, 1, 0, this vector is linearly dependent on these two vectors, 2/3, 1, 0, 0. Okay. And plus B is 1/3 and 4, 3, and 0. We can briefly check, and this is true over here. Now, we are going to use our understanding about row elementary operations. We said these operations do not change the linear dependence or independence of the original vectors. So this is of column vectors. So what it means is that the relationship between these three vectors over here is exactly the same as the ones we had over here. So this one over here translate back into the original vectors. This is what we have. We have 2, 2, 1. This is the corresponding vector over here. The last one is equal to 2/3, and 1, 0, 0 is the first one. So we have 1, -1, and 2. And plus over here is 1/3 and 4, 8, and -1. So if we call these three vectors over here, say if we call these three vectors v1, v2, and v3, after these row operations, we get to these vectors, corresponding vectors to w1 and w2 and w3. Okay. And then we found out over here that w3 is equal to 2/3 and w1 and plus 1/3 w2. Okay. What it means is that this relationship is the same, it's preserved, or it reflects the original relation. So v3 must be equal to 2/3 and v1 and plus 1/3 and v2. Okay. Multiply 3 both sides, we can say, or this is the same thing as 3v3 is equal to 2v1 and plus v2. Let's try to see if this is the relation we have. Twice of 1, -1, and 2 plus one vector over here. This should be equal to 3 times of the last vector, 2, 2, 1. Okay, and we can easily verify this is correct because this is 2, -2, and this is 4. Okay, and this over here we add 4 and 8 over here, -1, and this is equal to the right hand side. We have 6 and 6 and 3. Okay, so we have finished this problem over here. We found these three vectors are linearly dependent. Not only they are linearly dependent, we found out this relation over here, this linear dependence relation over here. Or we can say this is simply 2v1 plus 2v2 and minus 3v3 is equal to 0. That's exactly the definition we have for linear dependence. That means you can find non-zero numbers so that the linear combination is exactly 0.